The wind screamed through the canopy as Hauptmann Hans-Werner Lersch eased the control stick forward, watching the airspeed indicator climb past 430 miles per hour. The captured North American P-51B Mustang beneath him, coded T9+CK, in yellow and dark green German markings, responded to his touch with a smoothness that made his throat tight. It was June of 1944, and Lersch, one of the Luftwaffe's most experienced test pilots, had flown more than 80 different aircraft types in his career at the Rechlin test facility. But this machine was different. This machine was making him understand why German fighter pilots over the Reich were dying. The morning had started with skepticism. When the American fighter had been towed onto the circular turf field at Rechlin 3 days earlier, Lersch had walked around it with the careful attention of a man examining a opponent's weapon. The P-51B had belonged to Lieutenant Thomas Fraser of the United States, Army Air Force's 4th Fighter Group. On the 6th of June, D-Day itself, Fraser had made an emergency landing near Cambrai in occupied France, setting the aircraft down intact in a field. The Germans could hardly believe their fortune. Here, sitting on German soil with barely a scratch, was the fighter that was systematically destroying the Luftwaffe over Europe. Lersch had studied the intelligence reports. Since late 1943, these silver Mustangs had been appearing in increasing numbers as bomber escorts. They could fly to Berlin and back. They could dogfight with Bf 109 seconds and Fu 190 seconds at any altitude. And most troubling of all, German pilots reported that the Mustangs seemed faster than they should be, faster than the performance figures the Luftwaffe had estimated. Now Lersch was going to find out why. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 2. Afternoon test flight was proceeding according to plan. Lersch had already completed the basic handling checks, takeoff performance, stall characteristics, control response. The Mustang flew beautifully. Its controls were light, almost delicate compared to the heavier German fighters he was accustomed to. The visibility from the bubble canopy was extraordinary. And the range, even on this test flight, the fuel gauges showed he could stay airborne for hours. But it was the speed that haunted him. At 18,000 feet, Lersch advanced the throttle to maximum continuous power and watched the manifold pressure gauge climb. The Packard-built Merlin engine, a license-produced version of the British Rolls-Royce power plant, roared at 3,000 revolutions per minute. The airspeed indicator continued its steady climb, 400 miles per hour, 410, 420. At this altitude, a standard Messerschmitt Bf 109 G6 could manage perhaps 386 miles per hour. An FW 190A8 might reach 408. The Mustang was pulling away from them both, and Lersch hadn't even activated war emergency power. He keyed the radio, transmitting his observations to the engineers on the ground at Rechlin. Height, speed, engine temperature, manifold pressure, every number was being recorded. When he finally leveled off and began his descent back to the test facility, Lersch felt a cold certainty settling into his chest. This aircraft was good, very good, too good. But the real test was yet to come. The Rechlin facility sprawled across the landscape of Mecklenburg, roughly 100 kilometers northwest of Berlin. By mid-1944, it represented the heart of Luftwaffe aviation development and testing. The main airfield was unusual, a vast circular turf field, bounded by a hexagonal perimeter road, with no defined runways. Aircraft could take off and land in any direction the wind favored. Surrounding the field were laboratories, workshops, engine test cells, and housing for the engineers and test pilots who worked there. Rechlin had been Germany's primary aircraft testing center since the 1930s. Here, prototypes of every major Luftwaffe combat aircraft had been evaluated. The Messerschmitt Bf 109, the Junkers Ju 87 Stuka, the Focke-Wulf Fave 190, all had passed through Rechlin's systematic testing regime before entering production. The facility's test reports were considered the most reliable and objective performance data available. But by June of 1944, Rechlin had taken on an additional and increasingly urgent mission: evaluating captured Allied aircraft. As the air war intensified, more and more American and British aircraft were falling into German hands, some shot down and repairable, others making emergency landings on occupied territory. A special unit called Circus Rosarius, or Wonder Circus Rosarius, had been established to test these captured machines. The aircraft were repainted with German markings, their bellies and tail surfaces painted bright yellow for identification to prevent friendly fire, and assigned alphanumeric codes beginning with T9. The salvage and recovery operation itself was a massive undertaking. Specialized Luftwaffe recovery battalions, Bergbataillone, scoured occupied Europe for downed Allied aircraft. Speed was essential. Allied fighters routinely strafed their own crashed aircraft to prevent them from being recovered intact. Many potentially valuable specimens were destroyed by roving P-47 Thunderbolts or P-51 Mustangs before German crews could reach them. The aircraft that survived this gauntlet were transported to a repair center at Göttingen, where they were rebuilt using parts salvaged from multiple crash sites. By mid-war, Rechlin maintained stocks of captured Allied aviation fuel, lubricants, and even spare parts. The goal was to test enemy aircraft under conditions as close to operational as possible. When a B-17 Flying Fortress or a Mustang arrived at Rechlin, the engineers wanted to know exactly what the Americans could do, not what a captured aircraft flying on inadequate German substitutes might do. Hans Werner Lersch was the ideal man for this specialized work. Born in 1914, he had been drawn to aviation from childhood, building and flying model gliders, before progressing to full-sized sailplanes. His technical education and engineering background made him as much analyst as pilot. When he flew an aircraft, he didn't just feel how it handled, he understood why it handled that way. This combination of flying skill and technical knowledge had made him invaluable at Rechlin. By June of 1944, Lerche had already flown dozens of captured Allied types. He had tested a Supermarine Spitfire Mk2, noting its excellent turn performance, but criticizing its carburetor design that caused the engine to cut out under negative G-forces. He had flown captured B-17 Flying Fortresses, marveling at their exhaust-driven turbo superchargers that maintained power at high altitude. He had wrestled a B-26 Marauder into the air, nearly crashing during a hair-raising takeoff. Each aircraft taught him something about Allied design philosophy and capabilities. But the P-51B Mustang represented something different. This wasn't just another capable enemy fighter. This was the aircraft that was winning the air war over Germany. The strategic situation in June of 1944 was desperate for the Luftwaffe. Operation Overlord, the Allied invasion of Normandy, had succeeded on the 6th of June. American and British forces were ashore in France, and the second front that Germany had dreaded was now reality. In the skies over the Reich, American heavy bombers B-17 Seconds and B-24 Liberators were attacking in formations of hundreds of aircraft, escorted by swarms of P-51 Mustangs, P-47 Thunderbolts, and P-38 Lightnings. The Mustang, in particular, had changed the nature of the air war. Before its arrival in late 1943, German fighters could engage American bomber formations, confident that the escorts would have to turn back at certain distances. The P-47 Seconds and P-38 Seconds had range, but not enough to escort bombers all the way to targets deep in Germany. But the P-51B could fly to Berlin and back with fuel to spare. It could dogfight with Bf-109 Seconds and Fw-190 Seconds on equal or better terms. And increasingly, German pilots were reporting something else. The Mustangs seemed to have an advantage in power and speed that couldn't be explained by the airframe alone. Lerche had read these reports with professional interest. German intelligence had obtained reasonably accurate specifications for the P-51 wingspan, weight, armament, engine type. The Packard V-1650 was a license-built Rolls-Royce Merlin, an engine the Germans knew well from captured Spitfires. On paper, a Bf-109G or Fev-190A should have been competitive. In practice, German pilots were being shot down in alarming numbers. Now, with T9 plus CK sitting at Rechlin, Lerche and his engineering team had a chance to understand why. The test program for the captured Mustang was methodical and comprehensive. Over several weeks, Lerche and other test pilots would fly the aircraft repeatedly, measuring performance at different altitudes, speeds, and configurations. Every test flight generated pages of data speed versus altitude curves, rate of climb measurements, fuel consumption figures, handling characteristics, control forces. The Germans photographed every detail of the aircraft's construction, took apart its systems, and analyzed its design. Initially, the Mustang was tested with standard German aviation fuel. The Luftwaffe primarily used two grades: B4, a synthetic fuel produced from coal with an octane rating of around 87, and C3, a higher performance fuel with a rating of approximately 96 octane by German measurement standards. The C3 fuel was precious and scarce, produced in limited quantities through complex chemical processes. Most German fighters used it, but supplies were never adequate. The first test flights with German fuel were enlightening. The P-51B performed well as intelligence reports had suggested. It was fast, maneuverable, and had excellent range. At various altitudes, it matched or exceeded the performance of the Bf-109G and Bf-190A. The engineers confirmed what pilots had reported. The Mustang was a formidable fighter, but something troubled Lerche. He had flown the Mustang hard, pushing it through maneuvers and high-speed dives. Yet he felt that the aircraft was not revealing its full potential. The engine ran smoothly, the controls responded crisply, but there was a sense impossible to quantify, purely instinctive that the machine could do more. The answer lay in a set of 55-gallon drums stored in a secure section of the Rechlin fuel depot. These drums contained captured American aviation gasoline, carefully preserved and analyzed by German chemists. The Americans called it 100-octane fuel, and later 100 over 130 grade, meaning 100 octane at lean mixture settings and 130 performance number at rich mixture. By mid-1944, the most advanced American fighters were beginning to use an even more potent formula, 100 over 150 grade fuel. The Germans understood octane ratings. They understood that higher octane fuel allowed an engine to tolerate higher compression ratios and higher manifold pressures without detonating the destructive engine knock that could blow holes in pistons. What they didn't fully appreciate was the magnitude of the advantage that American fuel technology provided. Germany's synthetic fuel industry was a marvel of chemistry and engineering. Through the Burgess process and Fischer-Tropsch synthesis, German chemists could convert coal into liquid fuels. The nation had abundant coal reserves, which made this technology strategically vital when access to petroleum sources became limited. The synthetic gasoline produced was actually quite pure, lower in sulfur and other contaminants than petroleum-derived fuels. But there was a problem. Producing high-octane fuel required additional processing steps, reforming, cracking, and the addition of costly chemical compounds like tetraethyl lead and aromatic hydrocarbons. Each increase in octane rating reduced the total volume of fuel that could be produced from a given amount of coal. Germany faced a cruel calculation. They could produce more fuel of moderate quality, or less fuel of higher quality. With fuel supplies already constrained by Allied bombing of synthetic fuel plants and the loss of Romanian oil fields, the Germans had limited room for choice. American industry faced no such constraints. The United States had vast petroleum reserves and had invested heavily in catalytic cracking technology. Plants across the American oil belt could produce high-octane aviation fuel in enormous quantities. More importantly, American chemists had perfected the production of tetraethyl lead and other octane-boosting additives. By 1944, American refineries were producing fuel that German engineers could barely imagine making in meaningful quantities. The difference was more than academic. Octane rating directly affected what an aircraft engine could do. Higher octane fuel allowed pilots to use war emergency power, temporary boost settings that increased manifold pressure far beyond normal limits. For a few critical minutes during combat, this could mean the difference between catching an enemy or being caught, between shooting down a bomber or being shot down by its escorts. On a morning in mid-June, the engineers at Rechlin prepared T9 plus CK for a different kind of test flight. The German fuel was drained from the Mustang's tanks. Carefully, methodically, mechanics filled the Kellic aircraft with American 100 over 130 octane fuel from the captured stock. The fuel had a distinctive green color from the dye added for identification. As it flowed into the wing tanks, the chemical difference between this fuel and the German B4 or C3 was invisible to the naked eye. But at the molecular level, it represented a gulf in industrial capability. Lerche climbed into the cockpit, ran through the pre-flight checks, and started the Packard Merlin engine. Everything seemed normal. The engine caught, settled into a steady rumble. Gauges showed normal readings. He taxied to the edge of the circular field and turned into the wind. The takeoff felt different immediately. As Lerche advanced the throttle, the engine responded with a surge of power that seemed sharper, more eager than before. The Mustang accelerated down the grass field and lifted off smoothly. As he climbed away from Rechlin, gaining altitude over the Mecklenburg countryside, Lerche began to understand that he was experiencing something significant. At 5,000 feet, he leveled off and began the first speed runs. The airspeed indicator climbed steadily faster than it had in previous tests with German fuel. At 10,000 feet, the difference was more pronounced. The same throttle settings were producing noticeably higher speeds, and the engine felt different. It ran smoother, pulled harder, seemed to relish the higher manifold pressures. Lurch climbed higher, to 15,000 feet, then 20,000. At each altitude, he flew precisely measured speed runs, while engineers on the ground tracked him by radio and visual observation. When he finally descended and landed back at Rechlin, taxiing the yellow-marked Mustang back to the test area, he knew that everything had changed. The data was undeniable. With American fuel, the P-51B was 10 to 15 miles per hour faster at every altitude. Rate of climb improved by hundreds of feet per minute. The engine could be pushed, harder, longer, with less risk of detonation damage. The Americans weren't just flying better aircraft, they were flying the same aircraft significantly better than German fuel could enable. The engineering team gathered to analyze the results. They ran calculations, compared performance curves, studied fuel consumption data. The conclusion emerged slowly, reluctantly, but with absolute clarity. The P-51 Mustang's superiority came not primarily from its excellent airframe design or even its powerful Merlin engine, but from the fuel that made the engine achieve its full potential. One of the engineers made a grim observation. If they put American fuel in a Bf-109G or Fair AW-190A, those German fighters would also perform better, perhaps 15 to 20% improvement in power output. But Germany couldn't make that fuel, not in the quantities needed, not while Allied bombers were systematically destroying synthetic fuel plants across the Reich, not while the chemical industry struggled to produce enough octane-boosting additives. The Americans could put their best fuel in every fighter, every bomber, every training aircraft. The Germans could not. This single fact, this invisible difference in the chemical composition of gasoline, represented a strategic advantage that no amount of pilot skill, tactical genius, or engineering cleverness could overcome. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. In the weeks that followed, additional captured P-51 seconds arrived at Rechlin for testing. Some were P-51Bs like Fraser's aircraft. Others were the newer P-51D model with its distinctive bubble canopy and 650 caliber machine guns. Each one underwent the same systematic evaluation. Each one confirmed the same devastating truth. Lurche flew several of these Mustangs. In his later memoir, a book titled Luftwaffe Test Pilot, Flying Captured Allied Aircraft of Dutch World War II, published in 1980, he would reflect on the experience with careful professionalism. He acknowledged the P-51's excellence as a fighting machine. He praised its aerodynamic design, its range, its pleasant handling characteristics. He noted that the cockpit was more complex than German fighters, with more controls and switches to manage. But he also understood, with the clarity that only direct experience could provide, that the Mustang represented more than engineering achievement, it represented industrial and scientific depth. The Americans could not only design excellent aircraft, they could power them with fuel that extracted every ounce of capability from those designs, and they could do it for thousands of aircraft simultaneously. Other captured Allied aircraft told the same story. When Rechlin tested captured Republic P-47 Thunderbolt's massive, powerful fighters with turbocharged engines, the performance on American fuel was startling. The P-47D could reach speeds exceeding 430 miles per hour and fight effectively above 30,000 feet. German pilots called it the Jug for its portly appearance, but they learned to respect its diving speed and devastating firepower. A captured Hawker Tempest, one of the latest British fighters, also impressed the German test pilots. Fast, powerful, and dangerous, it represented the evolution of British design philosophy. And like the American fighters, it ran on high-octane fuel that enabled performance German aircraft couldn't match. Soviet fighters captured on the Eastern Front presented a different picture. The Yakovlev Yak-3 and Lavochkin La-5 were excellent dogfighters, light, agile, and well-suited to low-altitude combat. But Soviet fuel quality was inconsistent, and these aircraft didn't have the high-altitude performance or the raw power that American fuel technology enabled. The pattern was clear. In the hierarchy of fuel technology, the Americans led, the British followed closely, the Germans struggled to keep pace, and the Soviets and Japanese lagged further behind. This hierarchy correlated directly with strategic bombing effectiveness, fighter performance, and ultimately, control of the air. By late 1944, German aviation fuel production was in crisis. Allied strategic bombing campaigns had targeted synthetic fuel plants with increasing intensity. Major facilities at Leuna, Politz, Brooks, and other locations had been hit repeatedly by American B-17 seconds and B-24 seconds, flying in massive daylight formations, and by British Lancasters and Halifaxes attacking at night. German industry was resilient, plants were repaired, production was dispersed, underground facilities were constructed, but the cumulative damage was severe. Fuel production statistics told a story of industrial collapse. In May of 1944, Germany produced approximately 316,000 tons of aviation fuel. By September, after intensive Allied bombing, production had fallen to just 17,000 tons, a catastrophic 94% reduction. Luftwaffe units across Europe faced fuel shortages so severe that training flights were curtailed, combat operations were limited, and newly produced aircraft sat on airfields unable to fly. The strategic bombing campaign against oil targets, what later analysts would call the oil campaign, was perhaps the single most effective element of the Allied air offensive against Germany. It didn't produce the dramatic visible destruction of city attacks, but it strangled the Wehrmacht's ability to move, the Luftwaffe's ability to fly, and the German war economy's ability to function. At Rechlin, the engineers studying the captured Mustangs understood these larger strategic realities. Their test reports were models of objectivity and technical precision. They documented speeds, altitudes, fuel consumption rates, and handling characteristics with Germanic thoroughness. The reports noted that captured American fuel stocks allowed for more realistic testing, and that performance with this fuel exceeded performance with German equivalents. But the reports also contained an undercurrent of resignation. The engineers could measure the advantage. They could quantify it in miles per hour, in manifold pressure readings, in rate of climb figures. What they couldn't do was eliminate it. Germany lacked the petroleum feedstock, the refining capacity, the chemical industry depth, and by late 1944, the time to match American fuel technology. The fuel disparity manifested in countless small ways that accumulated into strategic significance. American pilots could use war emergency power settings for 5 minutes during combat, enough time to chase down an enemy, execute an attack, and escape. German pilots had similar emergency power options using systems like MW-50 water methanol injection, but the boost was less, and the complexity of the systems made them maintenance intensive. American engines could tolerate higher boost pressures without detonation. The Packard-built Merlin engines in the P-51 could run at manifold pressures of 61 to 67 inches of mercury, more than twice atmospheric pressure, when using high-octane fuel and war emergency. Power. German engines running on C3 fuel could approach these pressures only with supplemental injection systems. And even then, the margins were tighter, the risks greater. The Americans could afford to be profligate with high-performance fuel. Training aircraft in the United States often used the same high-octane fuel as combat aircraft. There was enough production capacity to fuel not only fighters and bombers, but also the massive training establishment that produced tens of thousands of new pilots annually. Germany hoarded its limited stocks of C3 fuel for frontline fighters, while training aircraft made do with lower grades. The British had achieved similar fuel technology, though their path had been different. In 1940, during the Battle of Britain, the Royal Air Force had transitioned from 87-octane fuel to 100-octane fuel supplied by American refineries. The improvement in Spitfire and Hurricane performance had been dramatic speed increases of 30 to 40 miles per hour, rate of climb improvements of 500 to 1,000 feet per minute. German pilots who had dominated the skies over France in May of 1940 found themselves fighting improved British fighters in August and September. The fuel advantage hadn't been decisive by itself, but it had helped tip the balance. By 1944, British and American aircraft in Europe increasingly used 100 over 150 grade fuel, the same fuel that had transformed the captured P-51's performance at Rechlin. This fuel grade had been developed through collaborative work between British and American chemists. It used sophisticated blends of aromatics, alkylates, and tetraethyl, lead to achieve performance numbers that pushed the boundaries of piston-engine technology. The designation itself told the story. 100 octane at lean mixture settings, 150 performance number at rich mixture settings. The performance number scale extended beyond the octane scale, which ended at 100. A performance number of 150 meant the fuel could resist detonation 50% better than pure iso-octane under rich mixture conditions. This allowed engines to extract enormous power for short bursts, the kind of power needed to catch an enemy fighter or escape from danger. German chemists understood the theory. They had experimented with similar formulations. Late-war C3 fuel achieved performance approaching 100 over 130 grade in some batches, particularly those using iso-octane additives. But producing iso-octane required butene, which was also needed for synthetic rubber production. German industry faced constant trade-offs: fuel versus rubber, explosives versus fertilizers, steel versus aluminum. Every resource choice had cascading consequences. The Americans faced no such constraints. American industrial capacity in 1944 was staggering. The United States produced more than 96,000 aircraft that year, more than Germany, Britain, Japan, and the Soviet Union combined. American shipyards launched more tonnage in a single year than Germany had built in the entire war. American agriculture produced food surpluses that fed Allied armies worldwide. And American refineries produced high-octane fuel in quantities that would have seemed fantastical to German planners. Jimmy Doolittle, the famous pilot who had led the Tokyo raid in 1942 and who now commanded the 8th Air Force, had been instrumental in developing high-octane fuel technology years before the war. Working for Shell Oil in the 1930s, Doolittle had advocated for higher-octane aviation fuels. understanding that they would enable a revolution in aircraft performance. His million-dollar blunder, as skeptical Shell executives had called the high-octane development program, had proven to be one of the most consequential investments in aviation history. The catalytic cracking processes developed by Eugene Houdry and others in the late 1930s had made mass production of high-octane fuel economically feasible. The technology spread across the American oil industry. By 1944, refineries from Texas to California to Pennsylvania were producing tens of millions of gallons of high-octane aviation fuel monthly. Storage, distribution, and quality control were equally impressive. American fuel reached England in tanker ships, was stored in dispersed depots, and was delivered to airbases with careful quality assurance. Color coding systems prevented mix-ups: green for 100/130 grade, purple for the even higher grades. Fuel. Samples were regularly tested to ensure they met specifications. The entire system operated with industrial efficiency. Germany's fuel situation, by contrast, was increasingly desperate. The bombing campaign had destroyed not just production capacity, but also the supporting infrastructure: pipelines, storage facilities, rail connections. Allied intelligence, aided by ultra-decrypts of German communications and aerial reconnaissance, could track fuel shortages almost in real time. When German fighters appeared in smaller numbers or with less aggressive tactics, Allied analysts knew it reflected fuel scarcity rather than German strategic choice. The human cost of the fuel disparity was measured in pilot casualties. German fighter pilots in late 1944 faced opponents with every advantage: numerical superiority, better fuel, often better aircraft, and increasingly, the confidence that comes from sustained success. Luftwaffe losses mounted. Experienced pilots died or were wounded at a rate training could never replace. Inexperienced replacements arrived at combat units with minimal flying hours, sometimes less than 100 hours total time, because fuel shortages had curtailed advanced training. At Rechlin, Lerche and his colleagues continued their work through the summer and autumn of 1944, even as Allied bombing threatened the facility itself. In April of 1945, American heavy bombers, B-17 seconds and B-24 seconds from the 8th Air Force, attacked Rechlin with devastating effect. The circular test field was cratered, buildings were destroyed, and much equipment was lost. What remained was blown up by German forces before Soviet troops arrived on the 2nd of May. By then, Lerche had already evacuated, flying a Dornier Do 335, one of Germany's last advanced piston-engined fighters, to Allied-controlled territory in the war's final days. He survived the war and later emigrated to the United States, where his expertise in test flying found new application in the Cold War aviation industry. The captured P-51B that Lerche had flown, T-9+CK, had a different fate. Records suggest it remained at Rechlin, or one of its satellite fields, until the facility's destruction. Whether it was destroyed in bombing, deliberately demolished by retreating Germans, or captured intact by Soviet forces remains unclear. Like so many artifacts of that desperate period, its physical trace disappeared into the chaos of Germany's collapse. But the lessons learned from testing that aircraft and the dozens of other captured Allied machines evaluated at Rechlin survived in technical reports, in pilot debriefings, in the memories of those who had participated. German engineers had confirmed what their pilots already knew from combat. They were fighting an enemy with not just numerical superiority, but technological and industrial advantages they could not match. The fuel revelation carried implications beyond the immediate, tactical situation. It illuminated a fundamental truth about modern industrial warfare. Wars are won not just by soldiers or even by generals, but by scientists, engineers, and industrial workers whose contributions never appear in combat reports, but whose work determines what is possible on the battlefield. Consider the chain of causation. American chemists develop high-octane fuel. This enables aircraft engines to produce more power. This translates to faster, higher-flying fighters. These fighters escort bombers deep into Germany. The bombers destroy German industrial capacity, including fuel production. This forces German fighters to operate with inferior fuel. Their reduced performance makes them more vulnerable to the high-octane fueled Allied fighters. The cycle reinforces itself. By early 1945, the Luftwaffe's situation was catastrophic. Fuel shortages were so severe that fighters often couldn't respond to Allied bomber raids, even when aircraft and pilots were available. The introduction of jet fighters, the Messerschmitt Me-262 and Arado R-234, offered hope of technological leapfrogging, but jets required different fuel, kerosene-based J-2, and came too late in too small numbers to affect the outcome. The Strategic Bombing Survey, conducted by Allied investigators after Germany's surrender, documented the fuel crisis in detail. German aviation fuel production had been 663,000 tons in March of 1944. By March of 1945, it was effectively zero. The entire aviation fuel production infrastructure had been destroyed or captured. German forces in the war's final battles operated with whatever stocks remained, hoarded like gold, used drop by precious drop. Japanese aviation faced similar fuel problems, though from different causes. Japan had no domestic petroleum and limited coal. The nation had depended on oil imports from the Dutch East Indies and other conquered territories. American submarines systematically destroyed Japanese tankers, strangling fuel supplies to the home islands. Japanese aviation fuel quality declined throughout the war. Where Japanese fighters had started the war using 87 to 91 octane fuel, by 1945, they were sometimes using fuel of 70 or 80 octane, barely adequate for automobiles, let alone high-performance aircraft engines. The Soviet Union's fuel situation fell between the German and Japanese extremes and the American-British abundance. Soviet refineries produced adequate quantities of fuel, aided by American deliveries under Lend-Lease, but quality remained inconsistent. Soviet fighters generally used fuel in the 87 to 95 octane range. This was sufficient for the low-altitude, close support missions that characterized much Eastern Front combat, but it limited high-altitude performance. The Americans, meanwhile, pushed fuel technology even further. By 1945, experimental batches of fuel reached performance numbers of 150 and above. Late-model P-51 HS, the fastest production Mustang variant, could exceed 487 miles per hour using this fuel. The Grumman F-8F Bearcat, designed as a lightweight interceptor, achieved similar speeds. Even these advances came late in the war, but they indicated the trajectory of American chemical engineering. Post-war analysis by American technical intelligence teams examined German fuel technology thoroughly. Teams of investigators visited captured synthetic fuel plants, interviewed German chemists and engineers, and studied production records. Their reports, classified at the time but later declassified, painted a picture of an industry that had achieved remarkable things with inadequate resources, but ultimately couldn't compete with Allied industrial might. One report, Technical Report 145-45, titled Manufacture of Aviation Gasoline in Germany, noted that late-war German fuel quality was actually quite sophisticated in some respects. The use of aromatics and specialized additives had produced fuel that performed better than its octane rating suggested. Under certain conditions, German C3 fuel approached the anti-knock properties of Allied 100/130 grade. But the report also noted that this achievement came at enormous cost. The complex chemical processes required to produce C3 fuel were vulnerable to disruption. Loss of a single critical facility could cripple production. Allied bombing had exploited these vulnerabilities systematically. The report's conclusion was stark. Germany had the scientific knowledge to produce high-performance fuel, but lacked the industrial capacity and raw materials to do so in militarily significant quantities once the bombing campaign intensified. The strategic implications extended into the post-war period. American and Soviet forces raced to capture German scientists, engineers, and technical documentation. The expertise gained in synthetic fuel production from coal would later inform American research programs, though abundant petroleum made such technology less urgent for the United States than it had been for Germany. For aviation historians and engineers studying the war decades later, the fuel factor emerged as one of the less visible but more significant aspects of Allied victory. Popular histories focused on dramatic air battles, ace pilots, and sleek aircraft designs. These were indeed important, but underlying all of it was industrial and chemical engineering that made superior performance possible. The story of the Germans flying a captured P-51 Mustang and discovering the fuel advantage became part of this historical understanding. It wasn't that German engineers were incompetent. Rechlin's test reports were rigorous and honest. It wasn't that German pilots lacked skill. Many were among the most experienced and capable aviators of the war. The problem was systemic and strategic. Germany couldn't produce what it needed in the quantities required, and Allied bombing ensured that existing production couldn't be sustained. Lurch's memoir, published decades after the war, provided valuable first-hand perspective on the testing program. His accounts of flying captured Allied aircraft were detailed and professional, free from propaganda or bitterness. He described the P-51 Mustang with respect, acknowledging its excellence while noting specific characteristics that a test pilot would observe: control forces, visibility, cockpit layout, engine response. What came through in Lurch's writing was a sense of professionalism transcending national loyalty. He was an engineer and aviator evaluating machines, recording data, seeking to understand. That the machines happened to belong to the enemy was almost secondary. His job was to fly them, measure their capabilities, and report honestly what he found. That honesty extended to acknowledging their superiority in many respects. Other Luftwaffe test pilots who flew captured Allied aircraft reported similar impressions. The consensus was that American fighters were excellent machines, well designed, robustly built, and devastatingly effective when properly fueled and maintained. British fighters were praised for their handling qualities and high-altitude performance. Soviet fighters earned respect for their ruggedness and suitability to Eastern Front conditions. But running through all these evaluations was the recognition that Allied aviation operated from a foundation of industrial and technical superiority that Germany couldn't match. It wasn't any single factor, it was the accumulation of advantages in fuel, in production capacity, in pilot training systems, in maintenance and logistics, in the sheer scale of operations. The P-51 Mustang became symbolic of this disparity. Here was an aircraft that combined British aerodynamic design, the Mustang's airframe, British engine, technology, the Rolls-Royce Merlin, American production efficiency, North American aviation built them by the thousands, and American fuel chemistry, the high-octane fuel that made the engine reach its potential. It represented the Allied coalition's combined strengths. By war's end, over 15,000 P-51 Mustangs had been built. They equipped fighter groups across Europe and the Pacific. They flew top cover for bombers, strafed ground targets, escorted photo reconnaissance missions, and engaged enemy fighters wherever they appeared. They became synonymous with American air power. The 8th Air Force's 4th Fighter Group, the unit that Lieutenant Fraser had belonged to when his P-51B was captured, became the top-scoring American fighter group in Europe, with over 1,000 enemy aircraft destroyed. Much of that success came while flying Mustangs. Other units achieved similarly impressive records. German pilots learned to respect the Mustang, though they sometimes found ways to exploit its vulnerabilities. The P-51's liquid-cooled engine was susceptible to damage. A single hit in the cooling system could force an emergency landing. German pilots tried to target the vulnerable radiator beneath the fuselage, but more often, the Mustang's speed, range, and numerical advantage overwhelmed defensive tactics. The post-war world saw P-51 Mustangs continue in service for years. The US Air Force used them in the Korean War. Smaller nations operated them into the 1950s and 60s. Racing enthusiasts bought surplus Mustangs and modified them for air racing, where they set speed records that stood for decades. Today, surviving P-51 seconds are prized warbirds, maintained by collectors and flying museums, reminders of a technological and industrial achievement. The broader lesson about fuel technology influenced post-war military thinking. The development of jet engines, which used kerosene-based fuels rather than high-octane gasoline, partially shifted the terms of the technological competition. But the underlying principle remained. In modern warfare, victory goes to nations that can not only design advanced weapons, but also produce the materials and systems that make those weapons effective. The Germans' testing of captured Allied aircraft at Rechlin represented a last attempt to understand what they were up against. By mid-1944, the data gathered could inform defensive tactics but couldn't change the strategic situation. The test reports documented Allied superiority with scientific precision, but knowledge alone couldn't produce the fuel, raw materials, and industrial capacity that Germany lacked. In the war's final months, as the Reich collapsed, Rechlin's role diminished. Allied bombers had destroyed much of the facility. Soviet forces, advancing from the east, threatened to overrun the area. German jet fighters, the Me-262 seconds, and others, represented the technological future, but that future had arrived too late. The piston-engined fighters that Rechlin had tested and evaluated were being swept from the skies by overwhelming Allied numbers and industrial power. When Soviet troops captured Rechlin in early May of 1945, they found the remains of Germany's premier aviation test facility. Cratered airfields, destroyed buildings, wrecked aircraft. Some equipment and personnel had been evacuated westward. Much had been destroyed to prevent capture. The Soviets salvaged what they could, including technical documents and any surviving aircraft and equipment. The knowledge gained from testing captured Allied aircraft became part of the technical intelligence that shaped post-war aviation development on both sides. American and British teams interrogated German engineers, studied captured German aircraft and equipment, and incorporated useful innovations into their own programs. Soviet teams did the same from their occupation zone. The war's technological competition continued in different form during the Cold War. For the pilots who had flown both Allied and German fighters, men like Hans-Werner Lersch, the experience provided unique perspective. They understood the strengths and weaknesses of different design philosophies. They had felt the difference that fuel quality made. They knew that warfare was ultimately about systems, not just individual machines or pilots. Lersch's later career in the United States brought interesting circularity. The German test pilot who had flown captured American aircraft during the war now worked for American aviation companies in peacetime. His expertise, like that of many German engineers and scientists, was valued by former enemies who recognized talent regardless of nationality. The legacy of the fuel disparity extended into energy policy and industrial strategy. Nations that aspired to military power recognized that petroleum access and refining capacity were strategic necessities. The Middle East's importance as an oil-producing region became central to Cold War geopolitics, partly because of lessons learned about fuel's military importance in World War II. Aviation fuel technology continued evolving after the war, though the trajectory shifted. Jet engines reduced the importance of octane ratings. Jets used essentially kerosene, not gasoline. But turbojet and turbofan engines brought their own fuel chemistry challenges. The principle remained: better fuel chemistry enabled better engine performance. For students of World War II, the story of German test pilots flying captured P-51 Mustangs and discovering the fuel advantage illustrates how warfare operates on multiple levels simultaneously. There were the visible battles, fighters dogfighting over Germany, bombers attacking cities and factories, armies clashing on the ground. But beneath these visible contests lay invisible ones, chemists competing to produce better fuel, engineers designing more efficient engines, industrial managers optimizing production. The Germans lost these invisible battles as surely as they lost the visible ones. They lacked the resources, the access to raw materials, the industrial depth, and ultimately the time to match Allied capabilities. The test reports from Rechlin documented this reality with painful clarity. In retrospect, the fuel disparity was part of a larger pattern. Germany and Japan challenged opponents with far greater industrial and demographic resources. They achieved remarkable things: advanced technology, skilled soldiers, tactical innovations, but ultimately couldn't overcome fundamental resource disadvantages. Once those opponents mobilized their full potential, the outcome became increasingly inevitable. The P-51 Mustang, flying on 150-grade fuel, represented that mobilized potential. It wasn't just an excellent aircraft, it was an excellent aircraft powered by fuel that Germany couldn't produce, built in factories that Germany couldn't match, piloted by men trained in a system that Germany couldn't sustain, and supported by logistics that Germany couldn't replicate. When Lerche pushed that Mustang to 490 miles per hour during testing, exceeding the performance achievable with German fuel, he was measuring more than aircraft specifications. He was measuring the gap between Allied and German industrial capability. He was documenting, with scientific precision, one of the reasons Germany was losing the air war. The data went into reports. The reports informed tactical decisions and strategic assessments, but by mid-1944, no report could change the fundamental situation. Germany was fighting a war it could no longer win, against enemies it could no longer match, with resources it no longer had. The fuel revelation at Rechlin was just one of many such revelations during the war's final year. German intelligence officers studying Allied equipment found similar disparities in electronics, in metallurgy, in precision manufacturing. Each disparity told the same story. Germany had fallen behind in the industrial competition that ultimately determined military outcomes. For the men who fought in the air over Europe, German pilots in their Bf 109 seconds and Fw 190 seconds, American pilots in their P-51 seconds and P-47 seconds, British pilots in their Spitfires and Typhoons, these industrial and chemical factors were distant abstractions. What mattered was the immediate. Can I catch that enemy fighter? Will my engine give me the power I need? Do I have enough fuel to get home? But those immediate tactical concerns were shaped by the distant industrial factors. The American pilot could push his engine harder because better fuel allowed it. The German pilot had to conserve fuel because shortages limited operations. These small differences, multiplied across thousands of sorties, determined who controlled the sky. By the spring of 1945, Allied air superiority over Germany was absolute. Luftwaffe fighters rarely appeared in significant numbers. Those that did were quickly overwhelmed. The Americans and British bombed targets almost at will. The war's outcome was no longer in doubt. Germany's synthetic fuel industry, once viewed as a triumph of chemistry and engineering, lay in ruins. The plants at Leuna, Politz, and elsewhere were heaps of twisted metal and broken concrete. Romanian oil fields that had supplied Germany early in the war were in Soviet hands. The fuel that remained was hoarded for the army's last desperate operations and for the handful of jets that could still fly. The P-51 Mustangs that had helped achieve this air superiority continued flying combat missions until the final days. They strafed German airfields, destroying aircraft on the ground. They provided top cover for reconnaissance flights over the shrinking Reich. They flew patrols over concentration camps as Allied ground forces advanced. When Germany surrendered on the 8th of May, 1945, thousands of P-51 seconds were still in service across Europe and the Pacific. They had proven to be one of the war's most successful fighter aircraft, perhaps the most successful. Their combination of range, performance, and reliability had made them indispensable to the strategic bombing campaign. The captured P-51 that Lerche had tested at Rechlin T9+CK was lost to history, probably destroyed in the facility's final days. But the lessons learned from testing it survived. They informed German understanding of Allied capabilities. They validated what combat experience had already suggested. the Allies possessed advantages that extended far beyond the cockpit. For historians analysing World War II decades later, the fuel factor emerged as a crucial but often underappreciated element of Allied victory. It wasn't as dramatic as D-Day or as memorable as specific air battles, but it was fundamental. Without high-octane fuel, Allied aircraft couldn't have performed as they did. Without the industrial capacity to produce that fuel in massive quantities, tactical advantages couldn't have been sustained. The Germans' discovery of the fuel disparity through testing captured aircraft was thus both revelation and confirmation. It revealed the specific magnitude of the advantage 10 to 15 miles per hour faster, hundreds of feet per minute better climb rate, higher operational ceiling. But it confirmed what was already becoming tragically apparent. Germany was fighting a war against enemies with overwhelming material superiority. That superiority didn't guarantee victory in every engagement. Skilled German pilots continued scoring victories throughout the war, but it shifted the odds in every engagement. Over time, over thousands of sorties, those shifted odds accumulated into strategic dominance. The story of Germans flying a P-51 at high speed and then admitting that fuel technology made it unbeatable thus encapsulates a larger truth about World War II. It was decided not just by soldiers and battles, but by factories and laboratories, by chemists and engineers, by the accumulated weight of industrial and technological capability. For the men who flew and fought, for the engineers who tested and analyzed, for the chemists who formulated fuels and the workers who produced them, the war was an all-consuming present. Only in retrospect did the patterns become clear. The lessons emerge. The full significance of decisions and developments become apparent. The P-51 Mustang, powered by high-octane American fuel, became an emblem of Allied air power, not just because it was well-designed or fast or long-ranged, but because it represented a system that worked. Design, production, fuel, training, logistics, all functioning together at a scale Germany couldn't match. When the war ended, roughly 175 P-51 Mustangs survived into private ownership. Today, they fly at air shows and races, living monuments to the men who flew them and the era that produced them. Each time one of these restored Mustangs roars past with its Packard Merlin engine at full power, it's worth remembering. That sound, that speed, that capability depended on more than aluminum and rivets. It depended on chemistry, on industrial capacity, on the invisible infrastructure that made victory possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The hangar at Rechlin was cold that morning in early 1944, but Flugkapitän Werner Mulders barely noticed. His attention was fixed on the massive aircraft before him, an American P-47 Thunderbolt, captured intact after an emergency landing in occupied France. The fighter sat under harsh electric lights, its olive-drab paint chipped and scarred, but otherwise complete. Mulders had flown nearly every German fighter type, had tested captured Soviet and British aircraft, and thought he understood the hierarchy of air power. But as he walked slowly around this American machine, running his hand along the cool metal skin, he felt something unfamiliar. Genuine uncertainty about what he was about to discover. The Thunderbolt dwarfed everything in the hangar. It was huge, absurdly huge for a single-engine fighter. The BMW 801-powered Focke-Wulf 190 that Mulders considered the pinnacle of German radial engine design looked almost delicate beside it. The American fighter's fuselage was as wide as a small room, its cowling massive and blunt. German intelligence reports had been contradictory. Some claimed the P-47 was a mediocre fighter, heavy and unwieldy. Others reported it diving through Luftwaffe formations like a falling anvil, impossible to catch, impossible to escape. Now, standing in this freezing hangar, Mulders would learn the truth. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The German aviation establishment had built its understanding of fighter design on specific principles. Speed came from streamlining and lightweight construction. Maneuverability required small size and low wing loading. Power was important, but beyond a certain threshold, diminishing returns set in. The Daimler-Benz DB605 engine that powered the Messerschmitt 109 produced approximately 1,300 horsepower, a figure German engineers considered close to optimal for a single-engine fighter. Push much beyond that, they believed, and you simply added weight faster than you added performance. The BMW 801 Radial in the FUR 190 pushed to around 1,700 horsepower in its latest variants, and even that was considered almost excessive, justified only by the Radial engine's superior durability and ease of maintenance. This thinking wasn't arbitrary. It was grounded in years of careful engineering and combat experience. The Messerschmitt 109 had proven itself in Spain, in Poland, in France, and in the early years over Britain and Russia. It was light, responsive, and when properly flown, deadly. The Focke-Wulf 190, introduced in 1941, had shocked the Royal Air Force with its combination of speed, firepower, and ruggedness. German pilots had outfought numerically superior enemies for years. The Luftwaffe's technical confidence wasn't baseless arrogance, it was earned through victory. But that confidence was about to be tested in a very specific way. Because the question that morning at Rechlin wasn't whether the P-47 was a good fighter. Combat reports had already answered that, reluctantly. The question was how. German pilots reported that Thunderbolts could dive away from anything the Luftwaffe could send against them. They could absorb horrific damage and keep flying. They operated at altitudes where German fighters gasped and struggled. Most puzzling, they seemed to carry enormous fuel loads and still maintain combat performance. How could such a large, heavy aircraft do these things? Mulders received permission to remove the cowling. This was the moment of truth. German intelligence desperately wanted to understand this aircraft, and the engine was the key. 2 mechanics worked with him, carefully removing the massive panels that enclosed the power plant. Even the fasteners were different American engineering, American specifications, everything unfamiliar. It took nearly an hour to expose the engine completely. When the last panel came away, Mulders stood motionless. The Pratt & Whitney R2800 double wasp sat before him like something from another world. It was an 18-cylinder, 2-row radial engine, each cylinder machined with a precision that immediately caught his eye, but it was the sheer scale that struck him first. The engine displaced 2,800 cubic inches, nearly 46 litres. By comparison, the BMW 801 displaced just under 42 litres, and the DB 605 barely 36. The American engine was simply larger, built to dimensions that seemed almost reckless. But size alone meant nothing. German engineers knew that displacement was just one factor in power output. What mattered was how efficiently you could extract energy from that displacement, how much fuel and air you could force through the cylinders, how much heat and stress the components could withstand, how reliably it all worked under combat conditions. Mulders began a systematic examination, and with each discovery, his understanding of American engineering philosophy shifted. The supercharger was a marvel of sophisticated engineering. It was a 2-stage, 2-speed system, meaning it used 2 separate compressor stages and could shift between different gear ratios depending on altitude. This wasn't revolutionary. The concept was understood, but the execution was extraordinary. The turbine wheels were precisely balanced, the intercooling system complex and efficient, the mechanical linkages robust yet refined. This wasn't a prototype or an experimental system. This was production engineering, meant to be manufactured by the thousands. Mulders called over the other engineers. They needed to document everything, but more than that, he needed confirmation that he wasn't misunderstanding what he was seeing. The engine's rated output, according to the data plate still attached to the accessory section, was 2,000 horsepower for continuous mains 80s operation. With water injection, a system whose plumbing melders could now trace through the engine bay, it could reach 2,300 horsepower for emergency power. Some variants, they would later learn, pushed even higher, approaching 2,535 horsepower for short bursts, 2,000 horsepower. As a baseline, not a theoretical maximum or a test-bed achievement, but the routine, reliable output of a production engine installed in thousands of aircraft. The number seemed impossible. The BMW 801D, pride of the German radial engine program, produced approximately 1,600 horsepower under optimal conditions. The latest 801 TS variant, still in development and featuring its own sophisticated supercharging, might reach 1,900 horsepower if everything went perfectly. And here was an American engine, already in mass production, already deployed across multiple theaters, casually exceeding that. But the shock wasn't just the raw numbers. It was what those numbers implied about American engineering and manufacturing capability. The R2800 wasn't a hand-built racer or a limited production special. Pratt & Whitney would eventually build over 125,000 of these engines. They would power not just the P-47, but the F-6F Hellcat, the F-4U Corsair, the A-26 Invader, the P-61 Black Widow, a whole family of combat aircraft. Each engine required precision machining of hundreds of components, careful assembly, rigorous testing. Each engine represented thousands of hours of skilled labor and sophisticated industrial processes. German industry in 1944 was struggling. Allied bombing had disrupted production networks. Critical materials were scarce. Skilled workers had been drafted or killed. Quality control was slipping. And yet here was evidence that American industry was producing engines of greater complexity and higher output in quantities that dwarfed anything Germany could achieve. The implications went far beyond a single aircraft or a single engine. This was a glimpse into the vast industrial machine that was arrayed against them. Molders spent the next several hours examining every accessible component. The magnetos were robust and well sealed against moisture. The fuel injection system was sophisticated, ensuring precise mixture control across the engine's operating range. The reduction gearbox that connected the engine to the propeller was a masterpiece of mechanical engineering, handling enormous torque loads while maintaining reliability. Even small details impressed him: the quality of the fasteners, the routing of the oil lines, the accessibility of maintenance points. This was an engine designed not just to produce power, but to do so reliably, to be maintained by ordinary mechanics under field conditions, to keep functioning even when damaged. The fuel system revealed another layer of American thinking. The P-47 carried internal fuel tanks with a total capacity of over 300 gallons, more than double what a Messerschmitt 109 carried. With external drop tanks, which were becoming standard equipment, a Thunderbolt could carry over 450 gallons. Even with that enormous thirsty engine, the aircraft had combat radius that exceeded most German fighters by a wide margin. American pilots could fly deep into Germany, fight, and return home. German pilots, by contrast, were increasingly restricted to defensive operations within range of their bases. But perhaps most revealing was something Molders almost missed. On the engine's data plate, along with the technical specifications, was a production date and a serial number. This particular R2800 had been manufactured in July of 1943. It was now early 1944, and this engine had already seen months of combat use before the aircraft's capture. Despite hard service, despite exposure to combat damage and field maintenance, the engine showed remarkably little wear. The cylinder walls, when inspected with a borescope, were smooth and evenly worn. The valve train showed proper adjustment. The bearings, when the engine was partially disassembled over the following days, revealed only normal operational wear. This wasn't just a powerful engine, it was a durable one, engineered to last. German engines, by contrast, were increasingly fragile. the Daimler-Benz DB 605 required careful maintenance and still suffered frequent failures. New engines coming from the factories showed declining quality, with rough castings and imprecise machining. Combat life between major overhauls was dropping. Pilots learned to baby their engines, to avoid full throttle except in emergencies, to nurse damaged aircraft home rather than risk a forced landing. The contrast with American engineering philosophy was stark. Over the days that followed, Mulders and his team conducted ground runs of the captured engine. They wanted to hear it, to feel it, to understand its characteristics. When the R-2800 first roared to life, the sound was overwhelming, a deep, throaty bellow that made the hangar walls shake. At idle, the engine's exhaust crackled and popped, each cylinder firing with mechanical precision. As Mulders advanced the throttle, the sound built to a sustained roar, thousands of controlled explosions per second, creating continuous thrust. The propeller became a disk of blurred motion, pulling enormous volumes of air through its circle. They ran the engine through its power range, checking manifold pressure, oil temperature, cylinder head temperature. Everything functioned exactly as designed. The supercharger engaged smoothly when they tested the high-altitude gear settings. The water injection system, when activated, produced a noticeable surge in power, the engine's note deepening as additional horsepower flooded through the cylinders. This was the sound that American pilots heard every time they engaged German fighters. This was the power that allowed them to dictate the terms of combat. When Mulders finally shut down the engine after the test runs, the silence in the hangar felt oppressive. He and the other engineers stood looking at the aircraft, at this massive American machine, and contemplated what it meant. The Luftwaffe had based its tactical and strategic planning on certain assumptions about air power. Those assumptions included the belief that German aircraft were qualitatively superior to enemy designs, that German engineering excellence could compensate for numerical disadvantage, that Allied aircraft were crude but numerous. The P-47 Thunderbolt challenged every one of those assumptions. Here was an aircraft that combined brute power with sophisticated engineering, that married enormous size with genuine performance, that represented both mass production and individual quality. And this was just one type. Intelligence reports spoke of other American fighters, the P-51 Mustang with its incredible range, the twin-engine P-38 Lightning with its unique configuration. Each represented a different approach to the same problem, each backed by the same industrial might. The R-2800 examination became a classified report that circulated among Luftwaffe leadership. It made reading uncomfortable. The engine's power output alone was startling, but the report's analysis of what that implied about American industrial capacity was deeply troubling. If the Americans could produce such engines by the tens of thousands, if they could casually exceed German power output by 40% or more, if they could do this while also building bombers, transport aircraft, trainers, and maintaining a two-ocean naval war, then the material balance of the conflict was even worse than pessimistic estimates suggested. Some German engineers proposed crash programs to match or exceed American engine output, but the brutal reality was that Germany lacked the industrial capacity, the raw materials, and increasingly the time to respond effectively. Projects like the Jumo 213 and the DB 603 showed promise, potentially reaching 2,000 horsepower or slightly beyond, but these remained limited production types, never achieving the reliability or the manufacturing scale of their American counterparts. The BMW 801F, intended to push toward 2,000 horsepower, faced endless delays and technical problems. By the time improved German engines reached operational units, the Americans had moved on to jet propulsion and even more powerful piston engines. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Mulders himself would continue testing captured Allied aircraft throughout 1944, each examination adding to his understanding of the technological gap. But the R-2800 remained the most psychologically significant. It represented a fundamental difference in engineering philosophy and industrial capability. German designs emphasized elegance, efficiency, doing more with less. American designs emphasized abundance, reliability, and overwhelming force. Neither approach was inherently superior in the abstract, but in the context of total war. With unlimited industrial production, the American philosophy proved devastatingly effective. The technical analysis at Rechlin was one thing. Understanding the P-47 inches, the abstract, as a collection of specifications and engineering solutions, was manageable. But for the pilots who faced Thunderbolts in combat, the experience was entirely different. The engine's power translated into tactical advantages that fundamentally altered the nature of aerial combat over Europe, and German pilots learned these lessons in the most visceral way possible through survival and loss. Oberleutnant Franz Stigler, a veteran pilot with multiple kills to his credit, encountered his first Thunderbolt formation in the spring of 1943 over the Belgian coast. He was flying a Focke-Wulf 190, at that time still considered superior to most Allied fighters. His formation had bounced a group of P-47 seconds that were escorting B-17 bombers at around 25,000 feet. The initial pass seemed promising. Stigler's flight dove through the American formation, guns hammering, and then executed what should have been a standard escape maneuver. A steep dive to rebuild speed, then a climbing turn to reset for another attack. But the Thunderbolts followed them down. This wasn't supposed to happen. German fighters were fast in the dive, the W-190 particularly so. Allied fighters, German pilots had been taught, were slower, less aerodynamic, unable to match German diving speed. Yet here were these massive American machines staying with them, even gaining slightly. Stigler pushed his Focke-Wulf to its limits, the airspeed indicator climbing past 400 miles per hour, the aircraft shaking as it approached compressibility effects. Still, the P-47 seconds remained in pursuit, their big radial engines pulling them through the air with relentless power. At around 10,000 feet, Stigler attempted his climbing turn. The Focke-Wulf 190 could climb well at low altitude, its powerful BMW 801 engine providing excellent low-level performance. But as Stigler hauled back on the stick, converting his diving speed into altitude, he glanced back and saw something that violated his understanding of fighter combat. The Thunderbolts were climbing with him, their massive propellers clawing for altitude, their energy state seemingly infinite. One P-47 pulled into position behind him, closer than any Allied fighter had managed before. Stigler broke hard left, then right, then dove again, desperate to shake the pursuit. Only when he reached ground level, hedge-hopping across the Belgian countryside, did the American finally break off, not because Stigler had outmaneuvered him, but because the Thunderbolt pilot had reached the limit of his escort radius and needed to return to the bomber formation. Stigler landed shaking, not from fear exactly, but from the cognitive dissonance of the encounter. Everything he had been taught about fighter combat, everything that had worked against Spitfires and Hurricanes, and even early Thunderbolts had failed. The American fighter had more power, more speed, more endurance. It had dictated every phase of the engagement. Stigler had survived through experience and luck, not through any advantage in his aircraft. Similar stories accumulated throughout 1943 and into 1944. The P-47's power advantage manifested in multiple ways. In diving attacks, Thunderbolts could reach speeds that German fighters couldn't match without risking structural failure. The Jug, as American pilots called it, was built like a tank. Its massive airframe could withstand diving speeds that would tear apart lighter aircraft. Messerschmitt 109 pilots learned to avoid diving contests with Thunderbolts after several incidents where German fighters suffered catastrophic structural failures trying to match American diving speeds. But the power advantage wasn't just about raw speed. It was about energy management, the ability to convert between speed and altitude to maintain combat effectiveness across a wide range of conditions. The R-2800's enormous output meant that P-47 pilots could climb rapidly after diving attacks, regaining altitude that would take German fighters much longer to achieve. In swirling dogfights, this translated into a consistent energy advantage. Thunderbolt pilots could choose when to engage and when to disengage. German pilots, increasingly, could not. The psychological impact was profound. Luftwaffe pilots had entered the war with confidence bordering on arrogance. They had better training, better tactics, and they believed better aircraft. Even as the war turned against Germany, even as losses mounted and experienced pilots were killed, there remained a belief that German quality could somehow compensate for Allied quantity. The P-47, more than perhaps any other Allied aircraft, shattered that illusion. Major Heinz Baer, who would end the war as one of Germany's highest-scoring aces, later described the Thunderbolt as the most dangerous opponent in the West. This wasn't because it was the most maneuverable the Spitfire could turn tighter. It wasn't because it had the best high-altitude performance the later P-51 Mustang excelled there. It was because the P-47 combined overwhelming power with ruggedness and reliability. You could hit them, Baer recalled, see strikes all over the fuselage, see pieces fly off, and they would just keep coming. And if you made any mistake, if you let them get any advantage, that enormous engine would pull them onto you, and there was nothing you could do. The ruggedness that Baer mentioned was directly related to the engine's power. Because the R-2800 produced so much output, Republic Aviation could afford to build the P-47's airframe heavy. The Thunderbolt featured armor protection for the pilot, self-sealing fuel tanks, redundant systems, and robust construction throughout. A Messerschmitt 109 might weigh around 7,000 pounds fully loaded. A P-47 could weigh 14,000 pounds or more, nearly double. Yet because of that massive engine, it still maintained competitive performance. The weight that would have crippled a German fighter was simply muscle in a Thunderbolt. German pilots learned to respect this the hard way. There are documented cases of Thunderbolts returning to base with hundreds of bullet holes, with cylinders shot out of the radial engine, with control surfaces damaged, with hydraulics compromised and still flying, still under control. The R-2800's radial configuration meant that battle damage to one or two cylinders didn't necessarily disable the entire engine. The remaining cylinders could keep producing power, albeit at reduced levels. Multiple Thunderbolt pilots reported limping home on engines that had lost 3, 4, even 5 cylinders to combat damage. A German inline engine, hit in the cooling system or the crankcase, would seize within minutes. The American radial would keep grinding out power. This durability had a compounding psychological effect. German pilots who scored what appeared to be solid hits on Thunderbolts, who saw their tracers striking home, who watched pieces separate from the enemy aircraft, would then see that same aircraft continue fighting or successfully withdraw. It created doubt. Did I really hit him? Are my guns effective? Are we outmatched? These doubts accumulated over time, eroding the confidence that was essential for aggressive fighter tactics. By mid-1944, the Luftwaffe's situation over Western Europe had become desperate. The Allied invasion of Normandy brought overwhelming air power to bear against German forces. Thousands of Allied aircraft operated over France, and among them were hundreds of P-47 Thunderbolts. They flew bomber escort, ground attack, and fighter sweep missions. Their presence was constant, oppressive, inescapable. German fighter pilots who had survived years of combat found themselves fighting a different kind of war. It was no longer about seeking combat and winning dogfights. It was about survival, about choosing when to attack and when to hide, about managing dwindling fuel and ammunition against endless waves of enemy aircraft. The P-47 seconds, with their enormous fuel capacity and powerful engines, could loiter over the battlefield for hours. German fighters had minutes of combat time before they needed to withdraw to refuel. The mathematical reality was brutal. The Americans could afford to lose the engagement and come back. The Germans could not. Werner Mulders, whose examination of the captured R-2800 engine had revealed so much about American capabilities, never flew combat against Thunderbolts himself. His role was technical evaluation, not frontline service, but he read the combat reports, heard the pilot testimonies, and understood what they meant. The engine he had examined in that cold hangar was not an isolated achievement. It was representative of American industrial philosophy: build it strong, build it powerful, build thousands of them. Quality through quantity, abundance creating its own superiority. The Germans tried to respond. Emergency fighter programs proliferated in the final years of the war. The Focke-Wulf TAR-152 was designed to compete at extreme altitudes. The Dornier Do 335 tried to achieve high performance through a unique push-pull twin-engine configuration. Jets like the Messerschmitt 262 promised revolutionary speed advantages. But these efforts came too late, with too little industrial support, to alter the course of the war. The Me-262, for instance, was genuinely superior to any Allied piston-engine fighter in raw performance. But it was produced in only tiny numbers compared to the thousands of P-47 seconds, P-51 seconds, and other Allied types, and it was plagued by unreliable engines, inexperienced pilots, and Allied air superiority that made even landing and taking off deadly undertakings. The R-2800 engine, meanwhile, continued its reliable service throughout the war and beyond. In the Pacific Theater, R-2800-powered F-6F Hellcats achieved the highest kill ratio of any American fighter, dominating Japanese aircraft with the same combination of power, ruggedness, and reliability that made the P-47 so effective in Europe. F-4U Corsairs, also powered by the R-2800, became the Navy's premier fighter bomber, serving not just through World War II but through Korea and beyond. The engine's design was so sound, its engineering so robust, that variants remained in production into the 1950s and in service even longer. After the war, when Allied intelligence teams captured German aviation facilities and documents, they found extensive reports on captured Allied equipment. The analysis of the P-47 and its R-2800 engine appeared repeatedly. German engineers had understood exactly what they were facing. They had measured the power output, analyzed the manufacturing techniques, documented the engineering solutions. They knew, technically and precisely, how far behind they had fallen. But knowing and being able to respond were entirely different things. In post-war interviews, surviving Luftwaffe pilots consistently ranked the P-47 among the most feared Allied fighters. Not the most beautiful, that honor usually went to the Spitfire. Not the longest-ranged, the P-51 Mustang claimed that distinction. But the most formidable in direct combat, the most difficult to damage, the most capable of converting pilot aggression into results. The Thunderbolt's reputation was built on that massive engine, on those 2,535 horses of American engineering, on the industrial capacity to produce them by the tens of thousands. The story of the R-2800 examination at Rechlin represents a larger truth about World War II. Germany entered the war with technological confidence and real engineering achievements. German optical instruments, chemical processes, metallurgy, and many areas of applied science were world-class. But war is not won by excellence in isolation. It is won by the combination of engineering, industrial production, resource availability, and strategic vision. The United States possessed all of these advantages, and the R-2800 engine demonstrated them in concentrated form. American engineering philosophy differed fundamentally from German approaches. German engineers sought elegance, efficiency, the optimal solution to engineering problems. This produced remarkable designs: the Me-262 jet fighter, the Type XXI U-boat, various advanced weapons systems. But these designs often required precision, manufacturing, rare materials, and careful maintenance. They were engineering masterpieces, but industrial nightmares. American engineering, by contrast, prioritized manufacturability, reliability, and abundance. The R-2800 wasn't the most efficient way to extract power from fuel. It was relatively heavy for its output and consumed fuel at a prodigious rate. But it was reliable, it was producible, and it was powerful enough that these other factors didn't matter. This difference in philosophy extended beyond aircraft engines. American shipyards produced escort carriers, Liberty ships, and landing craft in quantities that seemed impossible to German planners. American factories turned out trucks, tanks, artillery pieces, small arms in endless streams. American farms fed not just American troops but Allied forces worldwide. The material abundance that German POWs witnessed upon capture, the waste, the casual attitude towards supplies, the sheer volume of everything shocked men who had fought on reduced rations and patched equipment. The examination of that single P-47 Thunderbolt at Rechlin in early 1944 provided German engineers with detailed knowledge of one American weapon system. But the real revelation wasn't technical, it was industrial and philosophical. The R-2800 engine, with its massive displacement and enormous power output, represented a fundamentally different approach to war. It was brute force engineering, backed by brute force production, wielded with brute force tactics. Against this approach, German elegance and efficiency proved insufficient. By war's end, the Luftwaffe had been destroyed not primarily by technological inferiority, though that played a role, but by attrition, by fuel shortages, by the loss of experienced pilots, by the overwhelming numerical superiority of Allied forces. The P-47 Thunderbolt contributed significantly to this destruction. It shot down thousands of German aircraft, destroyed countless ground targets, provided bomber escort that made daylight strategic bombing viable, and dominated the skies over Western Europe during the critical campaigns of 1944 and 45. The men who examined that captured P-47 at Rechlin understood all of this, or most of it, even in early 1944. They could see where the trajectory of the war was leading. The reports they wrote were factual, technical, professional, but underlying the technical language was a deeper recognition they were witnessing the material manifestation of Germany's defeat, not in a single battle or a single campaign, but in the fundamental disparity of industrial capacity between the combatants. Werner Melders survived the war and worked briefly in aviation post-war before retiring. He rarely spoke publicly about his wartime experiences, but in private conversations with fellow engineers, he would sometimes describe that morning in the hangar at Rechlin, the moment when the cowling came off the P-47 and revealed the R-2800 engine. The slow realization as he examined each component and system, the grinding conclusion that German engineering excellence was being overwhelmed by American industrial might. It was, he said, like watching the future defeat the present. The P-47 Thunderbolt flew its last combat missions in the Korean War, more than 5 years after World War II ended. The R-2800 engine continued powering various aircraft types well into the Cold War. By then, jet engines had replaced pistons as the primary power plant for military aircraft, and the era of massive radial engines had passed. But for a crucial period in history, during the most destructive war humanity had fought, that engine, and the aircraft it powered, represented the cutting edge of air power. And for German pilots and engineers who encountered it, the R-2800 was more than just an engine. It was a revelation about the nature of the conflict they were fighting and the inevitable outcome it portended. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.